Hello everyone. Today we are going to analyze this frame using stiffness matrix method. Before analyzing, let us see the frame one time. In this frame, we have three different parts. In the span AB, we have a uniformly distributed load 9 kN per meter acting for the full span. In the span BC, there is a point load 24 kN acting at a distance of 3 meter from the point B. In the vertical member BD, we have a point load 10 kN. It is acting in the center. Length of AB is 4 meter. Length of BC is 5 meter. Length of CD is 4 meter. The moment of inertia for AB is 3I. The moment of inertia for BC is 2I. The moment of inertia for BD is I. This frame is a non-sway type frame because the fixed support in the point A will not allow any horizontal displacement. Now let us find the fixed end moments. First, let us find them in the span AB. In the span AB, there is a UDL 9 kN per meter. This UDL is acting for the whole span. The formulas for finding the fixed end moments are minus WL square upon 12 and positive WL square upon 12. After applying the values inside the formulas, we are getting MFAB and MFBA. Now let us find the fixed end moments in the span BC. In the span BC, we have a eccentric point load 24 kN. The formulas to find the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. When we apply the values inside the formulas, we are getting MFBC and MFCB. Now let us find the fixed end moments in the column BD. Here there is a point load 10 kN. This point load is acting in the center. The formulas to find the fixed end moments are minus WL upon 8 and positive WL upon 8. When we apply the values inside the formulas, we are getting MFBD and MFDB. In the Kani's method, we have to find the kinematic indeterminacy. For that, we have to check the supports and the joints. In the points D and A, there are fixed supports. In the fixed supports, there will be no slope and deflection. In this frame, there is only one joint, that is the joint B. In this joint, the beam and column is connected. In the joint B, there will be slope, that is theta B. In the point C, there is a hinged support. In the hinged support, there will be no deflection, but there will be slope. So in the point C, we have the slope theta C. In this case, the kinematic indeterminacy of the frame is true. Now we are going to make the fully restrained structure. We know that in the point B, we have the slope theta B. So in the point B, we have to give a fixed support. So there will be no slope. Also in the point C, we have the slope theta C. To avoid this slope, we have to remove the hinged support and replace with a fixed support. You can see that I have given a fixed support in the point B, and in the point C, I have replaced the hinged support by the fixed support. In this structure, in the joints and the supports, there will be no displacement because all of them are fixed. That is why this is called a fully restrained structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. We have the coordinates in the points B and C because in these points only we have the slope. We have to make the coordinates in the clockwise direction. Now let us see the formula to find the slope values. System displacement delta matrix is equal to K matrix inverse into P matrix minus PL matrix. Inside the delta matrix, we will have the slope values theta B and theta C. Inside the PL matrix and P matrix, we will have two values because in this analysis there are two coordinates. The size of the stiffness matrix will be 2 cross 2 because in this analysis there are two coordinates. In the given frame, in the points B and C, we are having the coordinates. In these coordinates, there are no moments developed because in this frame there is no overhanging. So inside the P matrix, we can just enter 0, 0. In this formula, we have found the P matrix. Now let us find the PL matrix. We know that the PL matrix is the moments developed in the coordinates due to the given load. In this frame, we have made two coordinates. The first coordinate is in the point B. In the point B, we have found three fixed end moments, M of BA, M of BD, and M of BC. We have to add the three of them. After adding, we are getting minus 4.52. The second coordinate is located in the point C. In the point C, we have found one fixed end moment, that is M of CB. Let us apply that. In this formula, we have found the P matrix and the PL matrix. Now we have to only find the stiffness matrix. Now let's see how to calculate the stiffness matrix elements. For that, first we have to apply the unit displacement, that is theta is equal to 1 in every coordinate. In this analysis, there are two coordinates. In the points B and C, we are having the coordinates. So we have to apply the unit displacement in these coordinates. Then we can use the formulas. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged, the formula is 2EI upon L. We have to be very careful. We have to apply this unit displacement in the fully restrained structure and not in the given frame. In the stiffness matrix, now we are going to find the first row. For that, in the first coordinate, we have to apply the unit displacement. Our first coordinate is located in the point B. In the point B, there is a fixed support. Let us assume that when we apply the unit displacement, this fixed support becomes a hinged support because in the fixed support there will be no displacement. When we apply the unit displacement, we have to remove all of the loads. You can see that I have removed all of the loads and I have applied unit displacement in the point B. In the point B, we had a fixed support, but after applying the unit displacement, it became a hinged support. Now let us see how to draw these curves. We are applying unit displacement in the point B. The point B is a joint. It is connecting the spans BA, BC and BD. So we have to make three clockwise curves. We are making the clockwise curves because we are making the displacement in the coordinate direction. We have made the coordinates in the clockwise direction. Towards the point C, we have to make one clockwise curve. Towards the point D, we have to make one clockwise curve. And finally, towards the point A, we have to make a clockwise curve. Then we have to see the direction of the arrows and then draw these curves. We have to give some gap between the fixed supports and the curves because in the fixed support there will be no displacement. You can see that I have given some gap. In the stiffness matrix, now we are going to find the values in the first row K11 and K12. K11 should be calculated from the first coordinate and K12 should be calculated in the second coordinate. Both K11 and K12 should be represented in the clockwise direction because we have made the coordinates in the clockwise direction. Now let us find K11. For that, from the point B, we have to look other ends. First, look at the end A. In the point A, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of BA is 4. The moment of inertia is 3I. So instead of I, we have to apply 3I. Now from the point B, let us look the end C. In the point C also, we are having a fixed support. So we have to apply the same formula 4EI upon L. Here length of BC is 5. Let us apply. The moment of inertia is 2I. So instead of I, we have to apply 2I. Now from the point B, let us look the end D. In the point D also we have a fixed support. So here also we have to apply the same formula 4EI upon L. Length of BD is 4. Let us apply that. For K11 we have three values. We have to add all of them. After adding we are getting 5.6 EI. Now let us find K12. For that, from the point C, we have to look other ends. For the point C, we have only one end, that is the point B. In the point B, there is a hinged support. If the fair end is hinged, the formula for the stiffness is 2EI upon L. Length of CB is 5. The moment of inertia for CB is 2I. So instead of I, we have to apply 2I. Finally, for K12, we are getting 0.8 EI. Now let us find the second row in the stiffness matrix. For that, we have to apply the unit displacement in the second coordinate. In the point C, there is a fixed support. But when we apply the unit displacement, let us assume that this fixed support becomes a hinged support. You can see that I have applied unit displacement in the point C. In the point C, we had a fixed support, but now it becomes a hinged support. Now let us see how to draw this curve. We are applying unit displacement in the point C. From the point C, we have to make a clockwise curve towards the point B. Then we have to see the direction of the arrow and draw this curve. we have to give some gap between the fixed support and the curve, because in the fixed support there will be no slope. You can see that I have given some gap. That is why the curve ends before the point B and it cannot continue after the point B. Now let us find K21. For that, from the point B, we have to look other ends. For BA, there will be no stiffness because there is no slope curve. For BD also, there will be no stiffness because there is no slope curve. Now let us look the end C. In the point C, there is a hinged support. If the fair end is hinged, the formula for the stiffness is 2EI upon L. Length of BC is 5. The moment of inertia is 2I. Finally, for K21, we are getting 0.8 EI. Now, let us find K22. For that, from the point C, we have to look at the point B. In the point B, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of CB is 5. And the moment of inertia is 2I. So instead of I, we have to apply 2I. Finally, for K22, we are getting 1.6 EI. In the stiffness matrix, we have found both of the rows. Let us apply the values. EI is constant. Let us keep it outside. In this formula, we have found everything. Let us apply them. EI inverse is 1 upon EI. We can add these two matrices. After adding, we are getting this. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and find the inverse. If you do not know how to find the inverse of a 2 by 2 matrix, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. Then we have to multiply these two matrices. After multiplying, we are getting theta B and theta C. Now let us make the slope deflection equations and find the final moments. First, let us make the slope deflection equations in the span AB. In these equations, first let us enter the fixed end moments. Length of AB is 4 meter. Let us apply that. The moment of inertia for AB is 3I. So instead of I, we have to apply 3I. In the point A, there is a fixed support. We know that in the fixed support, there will be no slope. So theta A will be 0. After applying the value of theta B, we are getting MAB and MBA. Now let us make the slope deflection equation in the span BC. No need to make the equation for MCB because we know that the point C is a simply supported end. There will be no movement. So MCB will be 0. Now let us make the slope deflection equation for MBC. In this equation, let us apply the fixed end moment. The moment of inertia for BC is 2I. So instead of I, we have to apply 2I. Length of BC is 5. Let us apply that. After applying the values of theta B and theta C, we are getting MBC. Now let us make the slope deflection equations in the span BD. In these equations, first let us enter the fixed end moments. Length of BD is 4. Let us apply that. In the point D, there is a fixed support. In the fixed support, there will be no slope. So theta D will be 0. After applying the value of theta B, we are getting MBD and MDB. In this analysis, We have found all of the moments. For MAB, we got a negative value. That means MAB is acting in the anti-clockwise direction. For MBA, we got a positive value. That means it is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anti-clockwise direction. We know that MCB is 0. For MBD, we got a negative value. That means it is acting in the anti-clockwise direction. For MDB, we got a positive value. That means it is acting in the clockwise direction. Now we are going to find the reactions. First, let us take the span AB and find out the reactions. In the span AB, there are two movements. MAB, which is acting in the anti-clockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to find out RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RA. The UDL is acting in the anti-clockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and distance by 2. Then we have two movements. The 8.2 movement is acting in the anti-clockwise direction, so it will be negative. The 19.59 movement is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 15.15 kilonewton. Then we can apply the rule sigma V is 0 and find out RB1. Now let us take the span BC and find out the reactions. In the span BC, there is only one movement, that is MBC, which is acting in the anti-clockwise direction. In this span, first I am going to find out RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5 meter, so 5 RB2. The point load 24 kilonewton is acting towards the point C in the anti-clockwise direction, so it will be negative and the distance is 2 meter. Then we have a movement which is acting in the anti-clockwise direction, so it will be negative. After the calculations, we are getting RB2. By applying the rule sigma V is 0, we are getting RC. We have calculated the vertical reaction in the point B 2 times. To find out RB, we have to add RB1 and RB2. After adding, we are getting RB, which is equal to 33.89 kilonewton. Now let us take the column BD and find out the reactions. In BD, there are two movements, MBD, which is acting in the anti-clockwise direction, and MDB, which is acting in the clockwise direction. In this span, first I am going to find out HB. For that, I am going to take moment about D. HB is acting in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 HB. The 10 kilonewton point load is acting in the anti-clockwise direction, so it will be negative and the distance is 2 meter. This moment is acting in the anti-clockwise direction, so it will be negative, and this moment is acting in the clockwise direction, so it will be positive. Finally, we are getting HB. By applying the rule sigma H is 0, we can find out HD. Now let us make the shear force diagram in the spans AB and BC. We have to make this diagram using the vertical loads and the reactions. Now let us make the shear force diagram in the column BD. Using the horizontal load and the reactions, we have to make this diagram. Now we are going to draw the bending moment diagram. First, let us make the free movement diagram. For the free movement diagram, we have to assume every span as a separate simply supported beam. Using these formulas, we can find out these movements and draw this diagram. Now let us make the end movement diagram. Using these movements, we can make this diagram. For making this diagram, we have to see the direction of the arrows and draw. Now let us combine the free movement diagram and the end movement diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.